Hello everyone, it's me again, Mrs. Hanson, picking up with lesson 2 of our chapter 20 on carbohydrates. In this section, we'll focus our attention on the cyclic forms of monosaccharides. When an aldehyde reacts with an alcohol, we learned that a hemiacetal is formed. And just taking us back into a previous chapter where we had studied section 16.8, this is just pulling from that as a review. We could see that an aldehyde, remember our carbonyl carbon is at the terminal end of the chain, is going to react with an alcohol. ROH represents the alcohol. We produced a hemiacetal, and we started our chapter even by labeling acetals and hemiacetal carbons in the monomers of monosaccharides. Notice this carbon is attached to two oxygens. One of them is an alcohol, and the other then leads out to more carbon. A hemiacetal forms. Well, what's interesting with monosaccharides and the formation of a hemiacetal is that the structure itself contains both an alcohol and an aldehyde, doesn't it? At carbon number 1, we see the aldehyde, and it typically the farthest chiral carbon, and we're just going to say furthest away from the aldehyde. That's where the same carbon we use to define if it was a D or an L configuration. That's the chiral carbon that's farthest from the aldehyde or farthest from the ketone. That's the alcohol that we use to react with the aldehyde to form a cyclic hemiacetal. The cyclic hemiacetal that forms is from the reaction of an aldehyde with an alcohol, but they just happen to be in the same structure. Draw this with me. Draw 1, 2, 3, 4, 5 carbon chain. And just as a review, this is not a monomer of a monosaccharide, but just a general review of a previous section from chapter 16. Let's redraw that by bringing carbon 1 and carbon 5 close together. So when you redraw that, here's your alcohol group at your aldehyde group at carbon 1, and then just begin to draw a 6-membered ring. Just begin to draw that. We're going to begin to draw a 6-membered ring where at the 6th member, the oxygen is placed in the top right of the 6-membered ring. And now at carbon 1, that was the aldehyde. Here's your alcohol group, 2, 3, 4, 5, and there is your acetyl group. At carbon 1, it is a hemiacetal. Carbon 1 is attached to an alcohol, OH, and it's attached to an OR group in this direction. So that very definition is the hemiacetal. The carbonyl carbon and the alcohol group react. Now with a monosaccharide, we see that we have both structures, both of those functional groups present in the same structure. So this reaction can occur very easily. When the carbon atom is part of the hemiacetal in a new chirality center, it's known as the anomer carbon. When an aldehyde and the alcohol are in the same molecule, a stable hemiacetal is formed. So just thinking about the general reaction you wrote for 20.3, the general reaction, aldehyde plus alcohol gave us a hemiacetal. All right, that shows a hemiacetal formation. Then on the next part where we drew, the next structure had us draw 5-hydroxypentanal. That was an alcohol group at carbon 5 and an aldehyde group at carbon 1. You redrew that structure to create the hemiacetal, and it was a cyclic structure. That carbon, as we go on in the notes, is now part of the hemiacetal group, and it's a new chirality center. It is now going to be referred to as the anomer carbon. Carbon 1, it will always be directly to the right of the oxygen. That's part of the ring. There, I've got that written for us. So 1, 2, 3, 4, 5, and then an alcohol group. Remember how we named that a moment ago? You called that 5-hydroxypentanal. 5-hydroxypentanal. The aldehyde is at carbon 1. The alcohol group is at carbon 5. And when you bond them together, right here, the anomeric carbon means that it's attached to an OH group and an OR group in both directions, making it a hemiacetal. It's a cyclic structure. Now notice that cyclic structure can have two forms. At the anomeric carbon, if the hydroxyl group is pointing down, we call it the alpha anomer. And if at the anomeric carbon, the hydroxyl group is pointing up, it's referred to as a beta anomeric carbon. We need to remember those. Alpha points down, beta points up at the anomeric carbon. And I have that listed for you there. The anomeric carbon with the hydroxyl group pointing down, known as alpha, pointing up is known as beta. Should we practice those? Locate the hemiacetal carbon in each of these compounds and just tell me if they're alpha or beta. So I'm going to use my highlighter and I'll use yellow. I want you to find the carbon that's directly to the right of the oxygen that's a member of the ring. Let me highlight the oxygens that's a member of the ring and tell you that's what you start finding. The oxygen that's in the ring, locate that first and then go to the right and find the carbon. And I'll label that in green. So as I highlight green, this is the anomeric carbon. Now, the anomeric carbon I highlighted in green. To know if it's an alpha or beta, remember that alpha points down and beta points up. So now I want to locate the OH group. It's pointing down. So this is an alpha anomer. Here in letter B, the hydroxyl group is pointing up on the anomer carbon, so this will be known as the beta anomer, as is letter C. So find the oxygen that's in the ring, go directly to the right of that position, and that will always be the anomer carbon. If the hydroxyl group is pointing down on the anomer carbon, we'll label that as an alpha anomer. And then if it's pointing, let's just make sure we said that right. Anomeric carbon pointing down is alpha, beta is pointing up. Pointing down is alpha, beta is pointing up. When we think about drawing the cyclic forms of a glucose molecule or any cyclic structure, we're going to place the oxygen atom in the top right corner of the hexagon. So I know I'm going to have a 6-membered ring, and at the top of the right corner, we place an oxygen. We're going to add the 6th carbon up here. So to the left of the oxygen atom, to the left of it, place the CH2OH group. The anomeric carbon is always one position to the right. This will determine if you have an alpha or a beta anomeric carbon, right? And just kind of thinking about what else is attached to each of those. Place the anomeric carbon on the first carbon clockwise. So this carbon here we've learned is always the anomeric carbon, which really will serve as the site of attachment as we move from a monomer to a disaccharide to a polysaccharide. As we start joining these together, we know that we'll start placing those in that position of connection at the anomeric carbon. And then all other substituents to the remaining carbons just go clockwise around the ring. If the hydroxyl group is pointing left on the Fisher projection, it always points up on the ring. If the hydroxyl group is pointing right on the Fisher projection, it will point down on the rings. Let me just kind of clarify. Let's say I'm working here and I'll say I have an OHH. And then over here, I'll say I have an HOH, and I'm just generally saying, for any type of isomer of a monomer sugar. We're saying if you see it pointing to the, if you're seeing it point to the left, as you do in this hydroxyl group, that it would point up. So if it's on the left, I'm going to place the hydroxyl group above the ring and the hydrogen below the ring. If, for instance, you see in the Fisher projection the OH is pointing to the right side, think of that as pointing down, and I would see that as the H going up and the OH going down. So this is important, and I would say memorize that. Remember that. Work to practice so much that you remember how to draw the cyclic structure. Shall we try one? Here we have a D-glucose, and I think maybe what I'll do is just go back and I'm going to draw what you see on your notepad page, and we'll draw it together so it's not so overwhelming. So give me just a moment to draw in. I just want to drop. I have a 6-carbon structure, so I'm going to go 1, 2, 3, 4, 5, 6. And of course we know that glucose is an aldehyde. At carbon number 1 is the aldehyde 2, 3, 4, 5, 6. And let me just kind of get these bonds ready on the chiral center, knowing that this guy is not chiral, so it's just CH2OH at the end. Carbon number 2 places the hydroxyl group on the right. Carbon 3 places it on the left. Carbon 4 and 5 both place it on the right side as well. So this is what you're looking at on your slide, and this is just called D-glucose. It is an aldo, right, hexose, just to kind of keep bringing those back to our mind, aldohexose. Now, when we go to convert this, we're going to place an oxygen on the top right corner and draw a 6-membered ring from there. Alrighty. Now, to the left of the position, I want you to just think, well, how do we number this? Here's 1, this is carbon 1, this is carbon 2, this is carbon 3, 4, 5. Carbon 5 contains the alcohol where the oxygen becomes part of the ring. So this highlighted oxygen here, if I make it green, you know that this is the oxygen where it comes from. From carbon 5 used to have an alcohol group. It now becomes the 6th member of the ring. Now it says, when I draw this, I can keep in mind that each one of these is going to have a structure up and a structure down. To the left of the oxygen in the ring, this is where carbon 6 gets placed, CH2OH. This right here is carbon 6. It's this guy right here. It's just above the ring. Here is the anomeric carbon. That means if I place the OH group down, then I've made an alpha anomeric carbon. And I'll redraw a beta in a moment. Alrighty, but if I choose to take the alpha position, the OH at carbon 1 will point down. Now what we just said is that was the alcohol, wasn't it? This was carbon 1, so the aldehyde turns to an alcohol, and if I point it up or down, I have the choice because it's at carbon 1 position. I can determine if it's alpha or beta. Carbon number 2, the alcohol is on the right side. Do you remember? If it's on the right, it points down. So my OH points down at carbon 2. Over here at carbon 3, this is on the left side. That means that it must point up. At carbon number 4, it points to the right in the Fisher projection, meaning that it must point down on your cyclic structure. And of course, carbon 5 doesn't have an alcohol any longer because its alcohol became part of the ring, but I just lead up to the CH2OH group that now becomes carbon 6. This is the alpha D-glucose cyclic structure. What would the beta form look like? Well, again, let's draw a 6-membered ring where the 6th member is always an oxygen to the top right side of your 6-membered cyclic structure. Each of these carbons has 2 bonds, so we have these lines. By the way, these are known as Haworth projections. Just so we can see what's coming up here. These are going from Fisher projections to Haworth projections. At the anomeric carbon, which is always the carbon directly to the right side of the oxygen in the ring, anomeric carbon, if I choose to place the hydroxyl group up and the hydrogen down, this is now known as the beta anomeric carbon. All of the other positions remain the same. Carbon 2 points down, carbon 3 points up. Carbon 4 points down. Carbon 5 leads to the unchiral, the 6th carbon, and that would be the beta anomeric D-glucose cyclic structure. We'll practice. I promise we'll practice some more. We've just drawn through that cycle, and I said I wanted to kind of go through that with you. The hydroxyl group at carbon 5 becomes the 6th member in the ring. So this is the 6th member of the cyclic structure. If I think about this oxygen on carbon 5, this was a hydroxyl group. It now becomes the 6th member. We said the anomeric carbon is always to the right, one position to the right of the oxygen. If it's pointing down, we called it alpha. If it's pointing up, we called it beta. You drew these 2 forms into your notes. Carbon 1, 2, 3, 4, 5, and then lead up to 6. Carbon 6 is out of the ring. And it will always point up. Alrighty. Remember, if it's on the right side, it points down, just like right here. If it's on the left side, it points up, just like we found over here. Those are the critical skills from going from a Fisher projection to a Haworth projection. This we could see, as we know, is called the Fisher projection. And these down here in the cyclic forms are known as the Haworth projections. And these really do go back and forth with each other. These Haworth projections from Fischer projections are in dynamic equilibrium. The anomeric carbon, always one position to the right of the oxygen. That's the sixth member of the ring. Carbon 1. It used to be the aldehyde. It is now the anomeric carbon. Position 2, 3, 4, 5. Carbon 6 is always out of the ring, above. These cyclic reactions are a dynamic equilibrium, and they're called mutarotations. To go from the Haworth projection, which is the cyclic structure, the anomeric carbon pointing down for the hydroxyl group gives us the alpha configuration. The chiral carbon at carbon number 5, the alcohol group, becomes the sixth member of the ring. And so if we just break that bond, and you're thinking about where to break it, it's right here between the oxygen on carbon 5 and the anomeric carbon at carbon 1. And you can go back and forth between an acyclic glucose structure and a cyclic glucose structure. It's in a dynamic equilibrium. That cyclization reaction exists, called mutarotation. Let's practice some of these. Again, the more practice, the easier they become. Here's a sugar called D-mannose. D stands for dextrose. It means the chiral carbon that's the farthest away is in the right side, just so we remember. Draw both anomers of D-mannose, both anomers, well, that's going to be the alpha and the beta. So we'll just remember we'll have to have one alpha and one beta. We have a 1, 2, 3, 4, 5, 6 carbon chain. To draw, I want you to place the oxygen in the top right corner and draw a 6-membered ring from there. Now, remember that each one of these will require a bond. So we're going to draw a line there on each one of those members. Carbon 1 is the anomeric carbon. If we draw the OH group down, we will have positioned ourselves for the alpha anomer. Now remember, at carbon 2, the hydroxyl is to the left. And if it's to the left, it must point up. So the OH at carbon 2 is pointing up. Carbon number 3 is also pointing up. Carbon number 4 must be pointing down. It's to the right on the Fischer projection, as is carbon 5. Remember, the alcohol group from carbon 5 is now part of the ring, so we don't worry about that. But carbon number 6 comes up above the ring, always, out of the ring and above. That is the alpha anomer of D-mannose. So what about the beta anomer? Well, that's just redrawing. Redraw another 6-membered ring. This time, of course, as I get ready to place my 3rd and 4th bonds on each carbon, to do a beta, the hydroxyl group will point up at the anomeric carbon. Carbon number 1 is the anomeric carbon. Everything else will be identical. Carbon 2, the hydroxyl group is pointing up. It was on the left side of the Fischer projection. Carbon number 3 also pointing up because it was the left side of the Fischer projection. Carbon 4 has it pointing down because it's on the right side of the Fischer projection. Carbon 5 doesn't matter because this oxygen is now part of the ring. At carbon 6, we place our non-chiral center, CH2OH, out of the ring and always pointing up. And that is your beta anomer of D-mannose. That's not too bad, is it? And that's exactly what we drew. Carbon 2 and carbon 3, our hydroxyl groups were pointing up. At carbon 4, your hydroxyl group was pointing down. Notice that in terms of where we're locating the anomer carbon, always at carbon 1 is the anomeric carbon. If it's alpha, the hydroxyl group points down. And if it's beta, the hydroxyl group points up. The two anomers from there. Oh, we're doing good work, aren't we? How about trying one on your own, pausing the video of D-galactose, draw an alpha anomer in your notes, and just come back to see if we match. You have a few examples. You can work ahead of me, drawing each of these into Haworth projections. Have you paused your video and are working ahead? Okay, welcome back. Let's see how you're doing. We have a 6-membered in a Fisher projection. We're asked to go from the Fisher projection to a Haworth projection, the cyclic structure. So I'm going to draw my 6-membered ring with oxygen in the top right corner. From there, I know to place bonds 3 and 4 at each carbon using straight lines up and down. To draw the alpha anomer, I know the hydroxyl group at carbon 1 will point down. The anomeric carbon points the hydroxyl group down. And that means it's the alpha anomer. Alrighty, so that's carbon 1. It becomes the anomeric carbon. Now let's decide if things will go top, bottom, based on if it's left or right on our group. So at carbon 2, it's pointing to the right. The hydroxyl group is on the right. That means it must point down. So this is carbon 1, 2, 3, 4, 5. And you'll know that carbon 6, the non-chiral carbon, is always placed out of the ring pointing up. At carbon number 2, we said the hydroxyl group must point down because it's on the right side. If it's on the left side, as carbon 3 and carbon 4 have, it points up. And there's your alpha anomer of this particular D-galactose. Did you try the next ones as well? Let's see what you did. The alpha anomer, 1, 2, 3, 4, 5, 6 carbons, so we need a 6-membered ring. I'll get my 3rd and 4th bonds at each of these carbons ready. Carbon 1 is always the anomeric carbon. If I want the alpha, its hydroxyl group will point down. Look at these. These are all on the same side. They're all on the right side. Have you remembered, if it's on the right side, it means point down. Just think about up, down, point up, point down. So the hydroxyl group will point down all around the ring. And of course, the non-chiral carbon at carbon number 6, always out of the ring and pointing up. Let's look at the beta anomer of our next example. We have a 6-membered ring, again 6-membered because there's 6 carbons here. Drawing my 6-membered ring, getting together my 3rd and 4th bond for each of these carbons. Carbon number 1 is always the anomeric carbon. If I want beta, it means that the hydroxyl group will now point up, the beta anomer. Looks like carbon 2, 3, and 4 are all to the left. That means they'll point up. carbon 2, 3, and 4 all have their hydrogens down and hydroxyl groups up. At carbon number 5, the hydroxyl group becomes part of the ring, remember, so it doesn't matter if it's left or right there. But then the non-chiral carbon, carbon 6, is always up and out of the ring. This is getting easier. Let's draw the alpha anomer of letter C. So again, I draw a 6-membered ring, oxygen in the top right. I'm going to get bonds 3 and 4 ready. Knowing that carbon number 1 is always the anomeric carbon. Remember how we're taking this carbon and forming a cyclic structure. So that's why it's saying it becomes a cyclic ring there. And we want the alpha anomer, so that means the hydroxyl group will point down. Carbon number 2 has it to the left, so it will point up. And then the rest of these will be down. And of course, at carbon 5, you lead up to the 6th carbon out of the ring, always pointing up. And that is an alpha anomer for that particular monosaccharide. We're getting so good at these, drawing 6-membered rings. Well, now let's change a little bit and look at a ketose. The cyclic forms of fructose, meaning that the aldehyde is no longer present. Instead, we have a ketone with 2 anomers, alpha and beta as well. Notice that we have a similar set of rules, but instead of a 6-membered ring, we have a 5-membered ring. So think about fructose. At carbon number 2, that is your that's your ketone, the carbonyl carbon. We're still locating the hydroxyl group on the chiral carbon that's the farthest away. And that's going to be the site of attachment for the ring, right? So this is now the ring. We have 1, 2, 3, 4, 5 members in our ring. Just as if we had a 6-membered ring where oxygen was part of the members, we still invite that oxygen in, but we just have fewer carbons since we're starting the carbon ring at carbon 2 instead of carbon 1. That means we have to draw little houses instead of hexagons for ketoses. Carbon number 2 now becomes the anomeric carbon. Right here, the anomeric carbon is the original ketone, and it's going to attach itself to the oxygen from carbon 5. So carbon 1 also has the non-chiral CH2OH, and we have another non-chiral carbon always out of the ring. We just happen to have 2 non-chiral carbons at carbon 1 and carbon 6. So that means on the anomeric carbon, we have a non-chiral alcohol, and we have a non-chiral alcohol over here. If at the anomeric carbon, the hydroxyl group is pointing up, it's still called beta. And if the hydroxyl group were flipped and pointing down, you'd still have an alpha anomeric carbon. Let's point out the difference. The anomeric carbon, when we had aldehydes, we simply had hydrogens. Instead of having another carbon there, each time we had hydrogens to determine if it was alpha or beta. Notice here, instead of having hydrogen, we have just another first carbon in that 5-carbon chain. So all the other rules apply. It's just that we're now connecting from carbon 2 to carbon 5, and we have 2 non-chiral carbons out of the ring. Let's give it a try. Let's draw the alpha and the beta of D-fructose in the Haworth projections. So let's just start. Let me just redraw. I'm going to put a new slide in, if I may. And I'm going to just redraw where we have CH. Oops, I need a pen. Patience, please. We have CH2OH leading down to your ketone, leading down to hydroxyl on the left, leading down to a hydroxyl on the right, leading down to another hydroxyl on the right, leading down to a CH2OH. 1, 2, 3, 4, 5, 6. Now, this is a keto hexose. That means that the anomeric carbon now comes from carbon number 2. We're going to draw a 5-membered ring where oxygen is at the top of the house. There is a 5-membered ring. Let me just highlight where that oxygen is coming from. It's from the farthest chiral carbon, and this is going to become your cyclic structure. So now, to the right of your ring is actually carbon 2. Here's carbon 3, here's carbon 4, here's carbon 5. Well, where is carbon 1? Well, it's out of the ring because it's non-chiral. Carbon 5 has a out of the ring because it's non-chiral. And here we're just going to set up all those bonds and kind of put together what we have. The anomeric carbon is now carbon 2. If I decide to place the OH down and the non-chiral alcohol CH2OH up, I've made the alpha anomeric configuration because the alcohol is pointing down. Let's look at carbon 3. Carbon 3 says the OH is to the left. Now, do you remember, is that up or down when we're drawing? If it's to the left, it points up. If it's to the right, it points down. Just remember to draw your arrow up, then down. So if it's at carbon 3, it needs to point up. At carbon 4, it would point down. And now what happens at carbon 5? Remember, carbon 5, it doesn't matter if it's up or down because it leads out to the other non-chiral carbon. Remember, it's out of the ring and always up. So here is your 6th carbon, which is non-chiral, out of the ring and pointing up. When I want to draw the beta configuration, I'll draw the 5-membered ring again, getting all of my configurations ready. The only difference now is that the alcohol would point up and the non-chiral carbon CH2OH would point down, and everything else is identical. This is the beta anomeric configuration. The OH is pointing up. And that's what we've drawn for the alpha and the beta anomeric configuration of D-fructose. When I draw a 5-membered ring, I finish the bonds with all the chiral centers. That didn't come out very neat, did it? Chiral centers here. Remember that if I want the alpha, alpha points the OH down, and both of those non-chiral alcohol centers would both point up in this example. And then we have an up-down configuration. And that should match what you've drawn in that section where it says, let's draw the alpha and the beta configuration of our fructose in a Haworth projection. Can you identify the anomeric carbon and indicate if it's an alpha or beta anomer? Well, the anomeric carbon is always directly to the right of the oxygen that's in the ring, always. Anomeric is always one position right of the oxygen in the ring. So I highlighted those in yellow. To determine if it's alpha and beta, we then decide where is the hydroxyl group. So here it's pointing down. Therefore, we know if it's pointing down, that's the alpha anomeric position. It's also pointing down in letter B, isn't it? So this would also be alpha, but it's pointing up in letter C, so that would be beta. We know that this is a ketose because it has 5 members and 2 non-chiral carbons. That's the clue to know that it's a ketone because there's 2 non-chiral carbons outside the ring. You can have the the opposite direction here. If you think about how to put this together back in your Fisher projection, if you go from Haworth to a Fisher projection, carbon number 1 would be a non-chiral carbon. Carbon number 2 has to be drawn because it's also a non-chiral carbon, so we'll lead it out as a ketone. Carbon 3, 4, and then 5. And here's carbon 6. Now to position yourself, carbon 1, 2, 3, 4, 5, 6. There's the 6 carbons. If I number those in red, you might see them better. 1, 2, 3, 4, 5, 6. So at carbon 6, 1, 2, 3, 4, 5, 6, just to see where they're coming from. Now here, I forgot the alcohol part. That is a ketone with 6 carbons. We know that it's a D configuration because that's the natural state. The D configuration is how we find sugars in nature, telling me that the chiral carbon farthest from that ketone is on the right side. That's the natural configuration, is the D, not the L, but the D. At carbon number 3, it's pointing up. Now, what does that mean on our Fisher projection? If it's pointing up, does that mean that it's on the left or the right? Well, you got it. It means that it's pointing left. Here it's pointing down on carbon 4, so you knew it was on the right. At carbon 5, there is no alcohol there. It's going inside the circle, and it's always the D configuration. So you will find that this position, the farthest from the ketone, is always on the right. That's the natural state. So we just went from a Haworth projection back to the Fisher projection quite easily. Notice that in letter B, to do the opposite skill, take the Haworth and go back to a Fisher. There's a 6 carbon, and I could number those so we can see 1, 2, 3, 4, 5, 6 carbons. This is a ketohexose, meaning that I'm going to have 2 carbons outside of the ring. Those are non-chiral carbons. And at carbon number 2, we have a ketone position. That gives us carbon 3, 4, 5 as chiral centers. At carbon number 3, it's pointing up, so we know to make the hydroxyl group go left. Carbon number 4 is also pointing up, so the hydroxyl group will also point left. Carbon number 5, its hydroxyl group is part of the ring, but I know that it will always be the D configuration. That's the natural state. The carbon number 5 is always pointing right. And of course, these would be hydrogens. Should we try one more just for practice? go from the Haworth back to the Fischer projection? Well, I can tell you that it's a hexoketose, meaning I have 2 carbons outside of the ring that are non-chiral. At carbon number 2, that's not chiral either because it's double bonded to oxygen. We have 3 chiral centers in fructose and its enantiomers. Now, at carbon number 2, 1, 2, 3, right here, this hydroxyl is pointing up, so that's to the left. This hydroxyl is also pointing up, so that's to the left. And this guy down here is also pointing to the right because that's the D enantiomer. The only difference between B and C is the alpha-beta configuration. They came exactly from the same Fischer projection. These guys are enantiomers. One's alpha, one's beta. In our next section, we talk about oxidation and reduction of our sugars. How long have we been talking? We've got 46 minutes. I think I'll keep going. If you need a break, certainly pause the video and come back when ready. But I'd like to include this short section in here as well. We'll look at reduction first. Reduction of an aldehyde carbonyl group will go back to produce the primary alcohol it comes from. I remember in our alcohol and in our aldehyde ketone chapters, we've learned that aldehydes are reduced to primary alcohols. I want you to remember to reduce means to add hydrogen. And the most common way that we add hydrogen is to use molecular hydrogen with a catalyst, typically of a metal. You can see PD sitting on the arrow. That stands for palladium. You could also see platinum or nickel or rhodium. Those are all surface catalysts for the addition of hydrogen. So to be reduced means to add hydrogen across the carbonyl carbon. Now, in the Haworth projection, they're unreactive. But remember, this is in a dynamic equilibrium. So the process of oxidation and reduction only occur in the Fischer straight chain projection, and it will not occur in the Haworth projection. So we have to redraw, just as in the skill we practiced a moment ago. If you're given the Haworth projection, redraw that back into the Fischer projection to find your new alcohol. The alcohol will never be cyclic. So here we have 1, 2, 3, 4, 5, 6 carbons in this chain called D-glucose. Remember here, the chiral carbon farthest from the carbonyl group is always pointing on the right side, giving us the D configuration. All we're doing is taking this carbonyl carbon and turning it back into an alcohol, and so this becomes still non-chiral, but it goes from the aldehyde to the ketone, and that is the absolute only difference. I can turn a glucose into what we call an alditol, which is actually a sweetener often used in what they call sugar-free gum or sugar-free candy. If you have like gummy bears that are sugar-free, they typically use sorbitol, and a common name of that is just a sugar alcohol. Notice that in a true sugar molecule, a carbohydrate monomer, monosaccharide, we have an aldehyde at carbon 1. But in an alditol, which is a sugar alcohol, it's been replaced as an alcohol group. But everything else is drawn exactly the same way. Reduction has occurred when the aldehyde turns back into a primary alcohol. And that's all we have to do as we're predicting products of reduction. Here we have D-xylose. D because the chiral center farthest from away is on the right side. Just reviewing every chance I get. We have 1, 2, 3, 4, 5 carbons in this monomer. And we're being asked to just reduce that So you would see adding hydrogen and the presence of a metal catalyst. We are simply going to redraw this structure exactly the same way with 5 carbons. At carbon number 1 is now an alcohol. At carbon number 2 and 3 and 4, everything's the exact same way, terminating with the last alcohol. So this, if you remember the vocabulary word, alditol, alditol. The aldehyde has converted to an alcohol, and it's also a sweetener. When something is said to be sugar-free, instead of having an aldehyde at carbon 1, it's been replaced with an alcohol at carbon 1, and everything else is exactly the same. And that's exactly what we did. Xylitol. Xylitol is the sugar converted into an alcohol. You break these 2 bonds, form 2 new bonds, and you come up with the primary alcohol, the product of an aldehyde reduction. How about you try some? In the presence of molecular hydrogen and a metal catalyst such as palladium, what is the outcome of each of these reduction reactions? Pause your video and work ahead. In letter A, we have 3 chiral carbons terminating with the CH2OH. And now up at the top you have exactly the same thing, CH2OH. All of the alcohols are on the right side. So I'll just redraw those, converting my aldehyde into an alcohol. It's as easy as that. This is called reduction, adding hydrogen. Here I have 1, 2, 3, 4 chiral carbons. 1, 2, 3, 4 chiral carbons, terminating with an alcohol at the end and having a primary alcohol at the start as well. And I'll just redraw at carbon 2, the OH is on the right. Carbon 3, it's on the left, as is carbon 4. Carbon 5 is on the right. And we've just converted our aldehyde into an alcohol. And in this last example, we have 2 chiral carbons terminating here with a primary alcohol, as well as at the start. The aldehydes convert to alcohols. Draw everything else exactly the same. Now, oxidation of an aldehyde is quite easy to accomplish by using Benedict's reagent. Now, this is something you've used in the lab if you remember your color change. In the presence of an aldehyde, such as the D-glucose possesses, the Benedict's reagent is actually blue in solution. When it's oxidized, you're adding oxygen. Or another way of saying that is removing hydrogen. Adding oxygen to carbon bonds or removing carbon to hydrogen bonds. When aldehydes are oxidized, we get carboxylic acid, COOH. At the terminal end, remember, oxidation occurs, aldehyde to carboxylic acids. So in the presence of an aldehyde, this Benedict's reagent is actually blue, and when it's been oxidized, it has turned red. And you went back and forth in the lab with seeing color changes from blue to red, letting you know oxidation has occurred when an aldehyde converted to a ketone. So here, carboxylic acid, I misspoke. Let me write that to be sure you wrote that correctly. Aldehydes are oxidized, and you can sometimes just see that with an O in a bracket on top of the arrow to represent an oxidizing agent. And a specific oxidizing agent that causes this to occur is called Benedict's reagent. Notice that copper went from a +2, and over here copper is now a +1. Copper is being reduced in this redox reaction. The glucose is being oxidized by adding more oxygen to the carbon. It's oxidized. Copper was reduced. Remember, wherever there's oxidation, reduction must also occur. And I want you to remember ketones cannot be readily oxidized since they have no hydrogen on them. So remember, an aldehyde, since it has a hydrogen on it, are easily oxidized. But a ketone has no hydrogen on it, and therefore we're really not thinking that it should undergo any type of oxidation process. And the truth is it cannot undergo oxidation unless it rearranges itself. And that's kind of exactly what we're going to show you now. When a ketone undergoes oxidation, it has to undergo rearrangement first. It has to convert into the aldehyde, which it can readily do. Notice that a ketone at position number 2 has no hydrogen on it. So I'm going to just rearrange carbon number 1 and 2 and redraw the structure exactly as it is. So just switch positions. And therefore you can redraw to convert into your carboxylic acid. So even though this is a ketone, it can readily rearrange to form the aldehyde and then go on to your carboxylic acid through the process of oxidation. When you see this on the arrow, you need to recognize that as Benedict's reagent. Benedict's reagent is an oxidizing agent. It forces aldehydes to convert to aldehydes to convert to carboxylic acids. So if we redraw, they're quite simple. Here we have an aldehyde, 4 carbons long. Aldehydes readily oxidize. So I'll just redraw the 4 carbons. I have 2 chiral centers, so I'm just going to draw those as Fisher projections. Redrawing the CH2OH at the end is a non-chiral carbon. We have OH on the right, followed by left at carbon 2, then 3. And now up here, we have a carboxylic acid. Cool, a COOH has formed. So letter A, the aldehyde readily oxidizes into carboxylic acids. And what will do that is Benedict's solution. So make sure you're seeing Benedict's solution as your oxidizing agent. How about letter B? Notice this is a ketone, and that means ketones do not readily undergo oxidations. They must rearrange first. And now I just want you to remember to switch C1 and C2 and just redraw. So here's 1, 2, 3, 4. I'm going to draw carbon 1 now as the aldehyde leading down to carbon 2 with an alcohol. And now carbon 3 drawn the exact same way. And here's carbon 4, the non-chiral carbon. So now that I've rearranged, I just simply change the position of the alcohol and the ketone functional groups. Just switch. And when you redraw, you'll turn this now into the carboxylic acid. So there's 2 chiral centers. Those will be the same. At the end is your non-chiral alcohol. And up here now, of course, is your carboxylic acid. The aldehyde converts into the carboxylic acid. Cool. That carbon is what's up here. Make sure I did that neatly enough. Carbon attaches up here, giving us the COOH, carboxylic acid, oxidation product of the aldehyde after the ketone converts. And that's what we drew here. We converted knowing that this is carbon 1, 2, 3, 4. We switch these two places. Carbon 1 now becomes an aldehyde, which will readily oxidize into the carboxylic acid. So rearrange first, followed by oxidation. Sitting on the arrow, you could see O for oxidation. You could see in the direction Benedict's solution, which contains the copper ion. Which aldonic acid is formed by oxidation of each of our monosaccharide? So again, I notice in structure A, this is an aldehyde, so it will readily undergo oxidation. I have 1, 2, 3, 4, 5 carbons, and I have 3 chiral centers, so I can just do crosses there. At the terminal end is a non-chiral carbon alcohol group. Carbon number 1 is going to oxidize into the carboxylic acid, and each of the chiral carbons placed their alcohols on the right side, so I'll just redraw those as is. That was it. The aldehyde oxidizes into a carboxylic acid. Letter B is also an aldehyde. Aldehydes oxidize quite readily into carboxylic acids in the presence of Benedict's reagent. This one had 2 chiral centers, terminating with a non-chiral alcohol carbon. And of course, that carbon 1 is the carboxylic acid. And both of these alcohols were on the right side as well. Now, letter C is a ketone, which means it doesn't readily oxidize unless I rearrange first. So I'm just going to redraw and just switch the positions to have an aldehyde group at the top and a new position with an alcohol now at carbon 2. So I just switched these positions. And let me redraw everything else as it's shown. I should make the O attached to the carbon. Another chiral carbon here and terminating here. So this is where I rearrange now into an aldehyde. So the ketone rearranges to make the aldehyde, and now I can just simply draw the oxidative process by terminating with COOH. I gotta be neater, I'm sorry. The carbon is on the link here. So COOH, OH on the right, OH on the left, OH on the left, OH on the right, and then terminating CH2OH down here. If that messes with you, sometimes I draw them OH, but I just realized that you know that oxygen is actually attached to the carbon, not vice versa. There. So again, we just rearrange the ketone, forming an aldehyde that will readily oxidize in the presence of Benedict's reagent, and forming the COOH, carboxylic acid, has now formed. And we've practiced with those 3. Aldonic acid is the aldehyde being converted into the carboxylic acid through the process of oxidation. You now are ready to do some reading, focus on health and medicine, monitoring glucose levels, and when you're through with that, come back for your next lesson on disaccharides, and that will pick up on your 14th page of your note pack. Good work here so far, about 2/3 of the way done in our unit.